Yeah, let me click continue. Yes, thank you for the invitation. And yeah, I have my coffee here, although it's early in the morning. So I will get my cake hopefully afterwards. So my talk is on how I learned to stop worrying about and loving lifting to infinite dimensions. These talks are always sort of challenging to give virtually. So if you want a PDF to follow along, feel free to click down here. Maybe I'll give it a second or two. And it's a PDF of the talk. Maybe one or two slides are slightly different, but it should be mostly the same. So, I should start off, by thanking all of my students who really are doing sort of the heavy lifting here. And in fact, I'll give a special shout out to Shreyas, who I think, has done a lot of the work here, and Patrick, who's done a lot of the work here at the beginning of the talk. And then at the end of the talk, it's Dan and Shun's work primarily. The thing that I always like to start speaking about is, how hard is it to get systems that are robustly autonomous? And, probably the best metric, or one of the best metrics we have, is, really looking at human driving. I don't have the stats from Europe, but I do have the stats from the United States. And, on the y-axis here are the number of fatalities per 100 million miles driven by vehicles in the United States. This is an amazing statistic. It's actually been collected for almost 100 years, actually more than 100 years now. The number of fatalities per 100 million miles has gone from about 24, okay, down to about 1. So it turns out humans are amazing at driving. And if we really want to be able to sort of compete while building sort of robots or autonomous systems, this is really the metric, one of the metrics that we should really be looking at. And frankly, the challenge here is that, the number of miles driven is really the big challenge. And, at the moment, we just aren't close at all. So, if I take a look here at Waymo, which has been doing probably the most driving, this is up until 2019. I think they have some more statistics in 2020. It slowed down a little bit. They've driven a cumulative total of 10 million miles. And that's mostly just in and around sort of Chandler, Arizona, which, if you've never been to the United States, is a warm, nice, pleasant place. It doesn't snow. And the weather is fairly good. The roads are fairly wide. This doesn't look like Sweden. This doesn't look like Ann Arbor, where there is snow and the roads can be small. And so, really, that stat from the previous slide is one that's collected in a really diverse and difficult areas of the world. And at the moment, we just haven't come close to trying to collect the right type of statistics to really show that these sort of empirical validations of autonomy are even close to good enough to compare against humans. So that's just driving. At least I am interested in all sorts of other autonomous systems. So that is, things like Cassie, or things like quadrotors, or things like manipulation robots. And, the thing that I'm really interested in is, can we develop really nice tools to be able to talk about robust autonomy for all of these different types of systems? In this talk, I'm going to primarily focus on sort of the control or planning task. And in that context, how do we really develop autonomous systems that are really robust, or where we can make really strong claims about the safety of these systems while they're doing trajectory planning or control? And to try to understand that, we can take a look at a really simple scenario. So, here is my ego vehicle, and here's some sort of obstacle out in the world. Most algorithms that we have for doing planning and control, the way that they think is basically by discretizing some type of optimization problem and basically finding a solution in some sort of discretized space. This could either be discretizing time or discretizing, actions. In any case, these plans that they generate by doing some type of optimization, they tend to, generate solutions that look like this when they're working really well. The problem is that in order to make them work quickly, we tend to discretize time pretty coarsely. And the question always is, if the coarseness is refined and we make it a finer and finer trajectory, does it get actually closer to something that is actually unsafe? And the question then is, there's sort of a balance between, getting something that is able to operate in real time and something that is actually provably safe. And the question here is, how do we balance between these two types of problems? Getting something that can operate quickly, and at the same time, something that is validated to operate correctly. And so, the thing that I'm really interested in doing is figuring out the right balance between these two. And one way to think about that is by looking at model fidelity in some way, or representing the particular problem that you care about in a really nice way. This can be kind of a challenge using typical techniques where I have a nonlinear dynamical system, I write down some sort of nonlinear program. That nonlinear program, I may have more and more decision variables, and that may represent safety better and better and better. But again, it's going to slow down the performance of the system. So instead, my group has really been looking at these techniques where we can rely on sort of infinite dimensional representations of this problem. And the really cool thing here is that, that infinite dimensional representation, it'll allow us to apply really nice tools from convex optimization to try and balance between performance and safety by representing different types of model fidelity in interesting ways. So in the first, sort of portion of the talk, and I should mention, these infinite dimensional representations allow us to go from nonlinear models to linear ones. But in the first portion of the talk, I'll talk about this technique that my students have developed that's called Reachability-based Trajectory Design. And it's a certain type of lift of this nonlinear models into a linear one, where we can generate sort of representations of these linear models that are outer approximations to the nonlinear model's behavior. And that outer approximation will allow us to say something about safety at runtime. And then the second portion of the talk, I'm going to talk about something where we're really able to do sort of data-driven optimization and generate something that looks like a Kutman operator representation. Again, this is going to be a linear representation of a nonlinear dynamical system. But the impressive thing here is that that nonlinear model, which is going to be represented in a linear basis or linear representation, is going to allow us to apply sort of traditional control techniques like model predictive control to doing real-time control of a soft robot. I may not get to this part. I have a lot of slides. I apologize in advance, but I'll try to sort of provide a high-level sort of introduction to both of these topics. We've applied this type of planning to a bunch of different systems. So in fact, I'm going to show you lots of videos of this working. So this is RTD, so the Reachability-based Trajectory Design. It's applied on a rover. This is my lab when we used to have a lab. And these videos are always going to look sort of the same. So I'm just going to walk through it now sort of carefully. So we'll have this robot planning view, which is, you can imagine in, Gazebo or in MATLAB or something. And we have a camera on the robot. We have sort of this random world on the right-hand side. And in fact, we're going to have something that I'm going to call a high-level planner that's generating waypoints. We're going to have obstacles that are going to typically be drawn in red. We'll have our robot, which is going to be drawn in blue. And we'll have this control parameterized reachable set. And I'm drawing the slice of the reachable set, meaning a particular trajectory or a particular control that I've applied in the corresponding reachable set of the system. And basically what this car is going to do is select different types of reachable sets that it has pre-computed in order to do planning. And this is actually going to be drawn from a continuous space rather than a discrete space. And so this is what it's going to look like now moving. This paper is now in IGR. I think it was just published this year. You can find a video that I've shown here. The link will always be down here on the right-hand side if you want to take a look. And so they'll try to randomize it. All the compute is done on board and it's able to operate safely. The cool thing here, again, this tool, this is a simple example, but we've actually been able to apply it on a more realistic system. So this is an EV that is operating on the University of Sydney campus. And here it's operating in a more dynamic environment where there's people moving around, and this is getting up to about 5 meters per second in this sort of quad area. And we're actually working with the University of Sydney now to use this algorithm to operate sort of a ferrying system for students in and around campus. Again, this was presented at RSS. The video is down here. So is it just restricted to ground vehicles? Actually, that's not true. We've actually been able to extend it to quad rotors. And so this is another paper that was in DSAC. Again, YouTube link down here. It's our lab. It can't go very fast, but we have this quad rotor down here, and it's doing sort of all the compute on board, and it's able to get through sort of these complex environments. I'll jump ahead a little bit here, and you're actually going to be able to see it going through more and more complex environments. This has to deal with some sort of aerodynamic effects. So it is truly sort of dealing with the fact that I may have a nonlinear model. And in fact, you're going to see that it's able to operate with, dynamic obstacles as well. And hopefully my students will play forward here. And so we have a virtual obstacle here that's not depicted in the real world. And then we have this moving obstacle here, which is depicted with this rover. All the compute is happening in real time. And in fact, we're able to do more interesting things here where we have even people moving around in front of it. And again, all of the planning, all the reachable set construction in terms of selection of the reachable sets is happening at runtime. And so you're going to see some fun stuff going on here. And we've actually been able to apply this to even more complex systems, like this manipulation robot. So this is a 7DOF robot. So this is going to be more or less a 14-dimensional state space model that's nonlinear. And again, it's doing all the planning at runtime. Again, the predictions here, I mean, it's drawing a reachable set here, which is the sort of volumetric box here. And the waypoints, earlier on, I was drawing these sort of black stars along the way. The waypoints now are generated by an RRT, and it's sort of it's drawn as this black, description or black manipulator configuration. And so you can see it up here as well. And then we have these sort of dynamic obstacles appearing, and it's doing all the planning, everything at runtime. And in fact, we've actually been able to extend it to even more complicated systems. And this is Cassie. And in this instance, we're constructing an even more complicated reachable set. And so it's able to do planning at this point. This is sort of right when COVID was about to hit the United States. So this is sort of where we sort of got to before basically our lab had to shut down. So that's going to be sort of the first portion of my talk. The second portion of my talk, I'm going to hopefully talk about the sort of Kutmanbased control. Initial versions of this paper were presented at RSS and then at TRO, and then there's actually an extension that's up on archive at the moment. And what we're able to do is use a Kutman-based model, which is another kind of lift, to basically do manipulation. And so this is an example of us being able to build a data-driven model. And then, it's able to pick up an object that's handed to it, and then basically is able to figure out the weight of the object at the end effector, and it's able to place it into the right bin. And all of this is happening in real time. So it's basically figuring all of this out on its own. And these models are notoriously difficult these systems are notoriously difficult to model and subsequently difficult to control. But in essence, all of this sort of lifting-based technique is able to allow the application of linear-based control techniques, and that allows us to do quite a bit in terms of controlling these systems using sort of a data-driven perspective. I see a question. Maybe I can take a quick look at that question. Oh, never mind. I thought it was Jana's slide comment. Okay, great. So that's actually going to be my talk, more or less. I'm going to talk about sort of this reachability-based trajectory design for provably safe planning. And then I'm going to talk about the Kutman-based modeling and real-time control. If anyone has any questions, feel free to post it on the chat box. I will try to take a quick look every once in a while to make sure that I'm keeping up with everyone. I'll start by speaking about background, and then I'll discuss theory and then implementation for the first portion of the talk. I'll mention that I'm going to focus primarily on the manipulation example. It'll turn out that a lot of the techniques that we're developing extend, as I mentioned, to quadrotors and ground vehicles and Cassie, et cetera. But I'll focus on the manipulator case because it can provide a lot of insight into how we're thinking about scaling some of these methods into more complex systems. So for those who aren't familiar, typically people applying sort of or trying to do control and planning in autonomous systems world usually try to break it up into sort of a hierarchy. There's a high level planner, which in sort of the autonomous vehicle case is generating sort of waypoints for you to follow. So this is sort of, you can imagine as something like Google Maps, is handing you turn-by-turn instructions. Subsequently, that information is passed to a trajectory planner. What that trajectory planner tries to do is basically execute those turn-by-turn instructions. So what that means is, I may get information to go down to the end of the road, stop, and then make a right. Well, how do I get down to the end of the road and then make that right? Well, the trajectory planner is essentially deciding how to do that. And then finally, I have a tracking controller that is basically trying to follow the trajectory that has been designed in the previous stage. This tracking controller basically has to manage, the powertrain dynamics and a lot of other complications. And so, while doing trajectory planning, if I have the entire powertrain model, in my hand, it turns out to be really challenging to do real-time planning. So basically, you make a decision to abstract the model at some level and basically use a simplified model here to generate a trajectory, and then cross your fingers and sort of hope that a tracking controller can actually follow that trajectory that has been planned. So for anyone working in sort of the verification or validation community, that seems really problematic. And so the question is, how do we actually make some strong guarantees about the trajectory planner or the tracking controller behaving as desired, right? And so, many people have thought about bringing in sort of safety at this tracking controller layer. And, that's a good idea. And in fact, lots of folks have worked on that. So, we've, in my group, sort of divided them into sort of these different bins. So the first bin of sort of approaches to doing sort of this validation of path planning are these methods called check methods. And what they try to do is basically look at some sort of pre-computed trajectory and essentially validate that that particular trajectory can be realized by the system in a safe way. There's a lot of methods to do this, and I'm not going to do a great job of covering all of them. If you're interested, please follow up with me. I can share millions of references about this. But one particularly beautiful class of methods are these Zonotope methods by Chris's PhD advisor, Matthias Althoff. He's done that group has done a really beautiful job of developing these methods to essentially do collision checks at real time. The sort of way that these methods work is by relying on sort of linearizations of a nonlinear dynamical system and essentially generating zonotopes around those linearized representations of nonlinear systems. And that zonotope is essentially describing what can happen for this nonlinear system when it's treated as a linear system plus disturbance. These methods work really well when the system looks really linear, okay? So basically that's sort of the trade that they make. If I can write down the dynamics as even a linear time varying system plus a small amount of disturbance, these methods sort of shine, okay? Now, other methods, have tried to correct, a particular control input that has been generated at runtime if they are detecting that it's going to run into some sort of unsafe configuration. These methods, there's lots of different names for them and lots of different, modifications of this approach. Reference governors are sort of a good place to take a look at. This paper that I'm mentioning here is a really good survey paper. And what it does is basically, detect when a particular reference trajectory is going to run into a problem, and then a governor steps in and modifies that. More recently, sort of extensions of this idea, slightly different, but extensions I would argue are these control barrier function methods. Aaron Ames, this is a really great tutorial paper that surveys sort of what's going on in the area. Sort of a similar principle, which is basically, I build some sort of barrier for the system. And if I'm detecting that my system is going to run into an unsafe configuration, well, in fact, what these control barrier function methods allow you to do is to solve a quadratic program at runtime to basically be able to modify the trajectory. This last set of methods are called fast track. And what they do is they look back at that hierarchy I presented earlier, and they basically treat that planning model as if it's a disturbance. And they basically try to solve a Hamilton-Jacobi-Bellman style formulation of the problem where they basically ask the tracking controller to basically overcome the disturbance that is the planning model. That's really great. It works, interesting. Well, the challenge is always with sort of these HJB equation methods is trying to scale it up to solve really difficult problems. Nevertheless, these methods can work well if you're in the right sort of situation. What I'd argue is that these correct methods, because they sort of shift the burden to the control level rather than the trajectory planning level, is that they tend to be a little bit more conservative. So, either I solve a quadratic program at just this instance in time, that modification may not allow me to plan sort of over a horizon. And that can create some greedy issues. And similarly, if I'm treating my tracking controller as having to overcome some sort of disturbance, that can create some issues associated with, maybe being too conservative in certain situations. So others have thought about bringing in safety at a slightly higher level, at this trajectory planner level. And in fact, there's been a bunch of different methods, sort of thinking about this. I'll highlight two of them. One are sort of these funnel library approaches, which is, developed by Ani Majumdar and Russ Tedrick. So when I was a postdoc at MIT, actually, Ani was working on this stuff. It's really cool. Basically, what they end up doing is selecting a finite number of possible trajectories and generating sort of sums of squares representations for, reachable sets around these finite pre-computed trajectories. What we're going to do is basically generate a continuum of trajectories. And essentially what I'm going to show is how you can scale this method up to dealing with lots and lots of or more complicated high dimensional systems, but also how do you deal with obstacle representations and actually make really strong guarantees about safety. And so that's sort of the delta here between the funnel library approach, where they're really sort of just focusing on ensuring safety at discrete time steps and using a discrete action space. And here we're going to focus on safety over all of time, so over a continuous amount of time. And we're actually going to have a continuous space of possible things that the planner is allowed to select from at runtime. I'm going to describe sort of at a high level how RTD works. So offline, and I'll have this robot here on the right-hand side that's going to sort of serve as a surrogate model for how these methods work. Offline, what's going to end up happening is I'm going to select sort of a trajectory parameter space. Each trajectory parameter is going to correspond to a behavior for the robot. And in fact, what I'm going to do offline is generate a reachable set for the system, and that's going to correspond to some sort of volume in the workspace of the robot. And then what I'm going to have at runtime is basically constraints that are going to appear that are only known at runtime, and that's going to correspond to a set of unsafe trajectory parameters, right? And in fact, what I'm going to do is show that I can write down a trajectory optimization problem. So suppose I have some sort of desired configuration I'd like the robot to get to. Well, that may correspond to a particular target, trajectory parameter. Well, I can write that down as some sort of optimization problem here on the left-hand side, and it's going to turn out that that optimization problem is fairly easy to write down with really nice constraint representations and really nice cost representation, which is going to allow for the application of really nice sort of gradient descent methods that I'm going to be able to run really quickly at runtime. So that's basically what it's going to look like. And then, I can do optimization in whatever way I care to do it, and basically, discover maybe the closest possible solution that I can find at a particular instance. But because of the way that I'm representing obstacles and the way that I'm representing this reachable set, I'm going to be able to show that any feasible solution to this optimization problem is actually safe. And because of the way I'm going to parameterize trajectories, I can always guarantee that I'll find a feasible solution. Okay, so that's going to be the story I'll tell. The cool thing, at least, is that we have this sort of high degree, reachability for a continuum and for high degree of freedom robots. And I'm going to show you how to represent obstacles to really ensure that you're generating something that is safe. So that's going to be sort of at a high level what we're going to do. I'll walk through the theory here, and then I'll walk through the implementation. So how's this going to work? So let's write down a model for the manipulator. So again, I'm focusing on manipulators here. The technique can extend, but I'm going to have a multi-dimensional robot here. I'm going to let QI denote the joint trajectory of a particular joint I. I'm going to write down the equations of motion like this. You can pull up the the Murray-Lee-Shastri book or the Mark Spong book or any book working this space. You can write down sort of this equations of motion for a manipulator. I'm going to make two assumptions here. The first one is I'm going to assume all joints are revolute. Turns out that isn't a serious assumption for us. In fact, in general, this technique can be extended. It's just revolute joints illustrate sort of the most complex thing in an easy enough way for this presentation. But in fact, if I give you a prismatic joint or a spherical joint, it'll turn out this technique will extend to that. And then the last thing I'm going to assume is that the model is fully actuated. In fact, that is also not a very serious assumption, but it'll allow me to do this presentation in a clean way. CASI is actually underactuated. So in fact, the methods that we're presenting here can extend to underactuated systems as well. Okay, so why do I care about this full actuation for this particular talk? Well, in fact, if the model is fully actuated and I can write down the equations of motion, well, if I assume that I don't have any actuation constraints, well, what I can do is, as long as I have a desired trajectory that matches up with my current trajectory or current joint velocity and joint position at time 0, well, I can track that desired trajectory perfectly as long as I use something like feedback linearization if my model is fully actuated, and I can write down the equations of motion. So again, if I have a desired trajectory and that initial velocity and initial position of that desired trajectory match up with my current position and current velocity just at time 0, well, then I can track that trajectory perfectly as long as I assume that my model is fully actuated, as long as I assume that I have no actuation constraints and I have a model of the system. Okay, those are 3 really serious assumptions, but we'll start there, and then I'll show you by the end of the talk how to extend or remove most of these except sort of this fully actuated requirement. So what we're going to do first is parameterize trajectories, as I mentioned. So I'm going to give you an example of how this trajectory parameterization is going to look. So the way that it's going to work is, I have this trajectory parameter space K. I'm going to assume, and this is an assumption, that one of the trajectory parameters is going to correspond to the initial velocity of my system. Okay? And then the rest of the trajectory parameters can correspond to anything. I'm going to select something that looks like Q double dot desired. In fact, could be anything that you wanted it to be. But this particular choice of trajectory parameter is going to be required, and we'll see why in a moment. Well, under this selection, what that would mean is that if I had a particular trajectory parameter, I'm going to, first start off here, and this is going to be sort of the y-intercept of my trajectory parameterization, and then, the velocity could be, or the acceleration could be something that looks like this. Well, what I'm going to assume is that this is defined over some tau plan or t plan, and then eventually my trajectory parameterization is going to bring my system to a stop. Okay, so what I'm going to assume is that my robot must find a new plan within T plan, and otherwise it continues executing its previous plan, and my previous plan is always going to bring my system to a stop. And the other assumption is that this Q dot 0 is going to be one of my trajectory parameters, and we'll see why in a moment. And For the sake of simplicity, I'm going to assume that my trajectories always begin at q equals 0. I can always rotate my system around to make that assumption satisfied without any difficulty. So what I'm going to do is I'm going to apply a lift. As I mentioned, we're going to use infinite dimensional optimization. This is going to be the first example of a lift that I'm going to apply. And the lift is basically I'm going to take my trajectory parameter, and instead of just plotting my trajectory parameters here, I'm going to plot the sine and cosine of my trajectory over time. So what that would look like here is if I give you a particular trajectory parameter over here on the left-hand side, well, if I take the sine and cosine of that, it's going to correspond to some sort of, trajectory on the circle on the right-hand side. Okay. So why is that going to be useful for me? Well, now if I give you a set of possible trajectory parameters, that's going to correspond to a set of possible trajectories on this circle over here on the right-hand side for this particular joint. And in fact, what I'm going to try to do is I'm going to actually try to compute the reachable set for this system. Okay, so I'm going to call this sine and cosine. I'm just going to call it S and C here so that I don't have to carry around too many variables. And what I'm going to do is compute a joint reachable set for this system. Okay, and I'm going to denote that joint reachable set with the script JI, and it's going to belong to some subset of R2 cross K. Technically, this should be on S1, but I'll pretend for a moment that S1 is a subset of R2 as I've depicted here on the right-hand side. So I'm going to try to compute this joint reachable set, and it's defined as there existing a T such that I can write down this equation, and it satisfies the dynamics that I had written down on the previous slide. The interesting thing here is if I look at the dynamics of the system, I can write it down as a linear time varying system. And because it's a linear time varying system, I get lots of interesting sort of reachable set tools that are going to allow me to compute this joint reachable set in a really accurate way. Okay, and we'll talk about that in the implementation section. But this lift, which looks really mild, meaning it doesn't look very complicated, it's allowing me to essentially extract a linear time varying system representation for the trajectory parameters in this C, S, and K space. And in that instance, basically, I'm going to be able to apply really nice tools to compute the reachable set of the system without having any problems associated with nonlinear dynamics or any of these other problems. So by translating the dynamics from the Q space into this cosine and sine space, I've applied a really simple sort of nonlinear lifting technique, but that lifting technique is allowing me to do really nice things with respect to reachable set computation. So how am I going to use that? That works for one joint. How do I use that at runtime for multiple joints? The idea is going to be simple. I'm going to compute a reachable set for each of the joints separately, and then I'm going to somehow compose them together at runtime. In order for that to work, what I'm going to do is I'm going to do an operation that I'm going to call slicing, which is I'm going to take my system at this instance in time and take its joint velocity at this instance in time, and I'm going to plug that in. And what that's going to do is basically select a slice of the trajectory parameter space. And now that's going to correspond to a reachable set along this sort of slice of the system. Then I'm going to take the next joint of the system and I'm going to do the same operation. I'm going to select a subset of the trajectory parameter space corresponding to the current joint velocity. Okay, and that's going to generate a reachable set for the system as well. And I'm going to do the same thing for the next joint. Okay, and what I'm going to do at runtime is compose those slices together by doing some sort of multiplication on the reachable set. And this operation here is going to be called slicing, where I'm basically slicing in the current velocity at time 0 of my planning. And then I'm going to stack the reachable sets together, and I'm going to call that operation stacking. And the question is, how do I do slicing and stacking in a way that allows me to do nice things with respect to reachable set computation? And that's basically the story here. Slicing and stacking simple reachable sets for each joint individually will allow me to construct a high dimensional reachable set of the entire arm. Okay, so how does that work? Again, I slice. Okay, well, that particular slice I can represent as a rotation matrix over here on the left-hand side. Basically, each slice in here is going to generate a reachable set for the system, which is going to generate a sine and cosine as a function of time. Once I do that, I'm going to get a rotation matrix over here as a function of time. And in fact, I can take that rotation matrix and basically slice in, and then basically take the link volume. And now, if I multiply that rotation matrix as a function of time times the volume, I'm basically getting the link volume as a function of time under that particular slice. I can do that with each joint. Okay, so for example, I can do this with just joint here. Okay, I'm assuming that the rotation matrices look in a certain way because of my revolute joint is organized in a certain way. Well, I can, again, construct the manipulator volume again by doing this type of operation. But now, what's wrong here is that I haven't described the origin of the second manipulator. So in fact, what I need to do is include the translation and the rotation of the first joint. Well, in fact, that's easy to incorporate because I can actually predict what the next joint location is by looking at the previous joint's link volume. And so if I can compute R1, P1 as a function of time, well, I can essentially add that in to the link volume of V2 by doing this operation here. And that'll give me the parameterized swept volume of the second link. And that's what I'm basically calling stacking. And in fact, you can repeat this operation over and over and over. And I can generate the stack for the next instance in time by basically adding up the effect of the second, the origin of this, or the end effector of the second link, right? And in fact, I can do this type of stacking operation at runtime in order to account for the initial joint angles and velocities of the system and basically generate a parameterized representation of the volumes of the system. And in practice, that's going to allow us to construct a parameterized reachable set of the arm at runtime. And we can use that to describe the trajectory optimization problem using really nice hard constraints. What do I mean by that? Well, suppose I had this sort of box over here on the left-hand side that is an obstacle that I can only see at runtime. Suppose I do this type of slicing operation. What I'm going to do then is basically generate this volume here on the left-hand side of what the object or what the arm is capable of doing. Well, now I can project my obstacle here over on the left-hand side. And in fact, that's going to correspond to some sort of trajectories, trajectory parameters that are unsafe for the system. And now what I can do online is if I have some type of desired configuration, well, I can write that down as this following optimization problem with some sort of cost that is minimized if I get to this particular configuration. And in fact, I'm going to show that we can optimize over this, safe space in a really nice way. So, I can run gradient descent or something that detect what the safe trajectories are or what the optimal trajectory that is safe here is. So that's sort of the theory of it, slicing and stacking. The question is, how do you compute these reachable sets? Like, this is a nice theory, but how do we actually implement this thing? How do we actually implement stacking and slicing? Like, it's going to depend so much on how these reachable sets look. And then the question is, how do we generate these hard constraints? Okay, so those are sort of the three big questions here, and I'm going to answer all of them in this implementation section. So the way that we're going to do that, because our system, as I mentioned, when I transfer it into the sine and cosine space, it looks like a linear time varying system. There are really nice tools, to generate reachable sets for linear time varying systems. And the Zonotope methods that I was describing earlier, coming out of Matthias Althoff's groups, and Chris has played around with quite a bit, allow us to generate reachable sets in a really nice way for linear time varying systems, as long as they're represented as zonotopes. And so how is this going to work? I'm going to define what a zonotope is. It's going to have a center, and it's going to have these generators. And these generators are basically, going to describe ranges that the system is going to, or the zonotope is defined over. Okay, so for example, I have my center, which is some vector in Rn, and then I'm adding together beta 1 times G1, beta 2 times G2, and beta 3 times G3, and beta is allowed to be anything between -1 and 1. And so what this set would look like is something like this on the right-hand side, just some sort of volume here. Okay, and in fact, there's really nice ways for me to take my linear time varying system. I select an initial zonotope for the initial states of the system. And then under the dynamics and under this trajectory parameterization, I can actually draw out a reachable set for the system that looks like this thing on the right-hand side. And I can use tools like Cora. This is the 2018 version. There's a 2020 version. I think there's been a 2016 and 2014 version. These all generate reachable sets for the system. You can hand it any nonlinear dynamical system, and it'll generate a reachable set as zonotopes for the system. But in fact, if you generate, if you have a linear time varying system, these zonotopes are really tight. And that's going to matter for us in order to do real-time planning without being too conservative. The way that these zonotopes are constructed is that they're defined, there's a finite number of them, and each of them describe the behavior of the system over some finite interval in time. So for example, this initial zonotope is going to be valid, for example, between T0 and T1. And what that means is that the reachable set of the system is going to be inside of the zonotope defined between T0 and T1. And similarly, there's going to be a zonotope that's defined between T1 and T2. And the reachable set of the system is going to be inside of the zonotope between T1 and T2, and so on, okay? And so again, you can hand this dynamics and this zonotope to Cora, and Cora will generate a zonotope representation for the system, again, by leveraging the fact that in this instance, it's a nice linear time varying system, and nice things can happen for reachable set construction under those assumptions. So in fact, you can prove this really nice theorem. The zonotope reachable set contains the joint reachable set of the system. So this zonotope reachable set is a conservative approximation for the true behavior of the system. Interestingly, I can slice in trajectory parameters at runtime. So again, if I have a particular initial velocity of the system, I can actually slice that in at runtime to be able to generate a subset of this zonotope. So how does that work? Well, in fact, what the slicing operation corresponds to is to me fixing a particular zonotope coefficient value to some number. So in this instance, I may select it to be 0.50. When I do that, I'm generating a subset of the zonotope here on the right-hand side, okay? And so that zonotope slice is going to be something that I can then use at runtime, and it's just some subset of the zonotope here that I can actually use in a nice way, as I'll show. So what do? I'm going to slice, again, corresponding to my initial velocity, and that's going to generate some subset of the reachable set, the zonotope reachable set on the right-hand side. And in fact, what I can do now is basically transform that slice into a matrix. So remember, it's generating signs, the sine and cosine values over time. Well, I can transform that into some sort of matrix. And in fact, the thing I'll need in order to be able to understand how that looks is to define something called the matrix zonotope. It's the same thing. It's just now my center is now a matrix and my generators are matrices. You can just think of this as sort of the extension of everything to R n by n. Nothing crazy happens here. So now if I want to understand how to do stacking, the idea is really simple. I have my volume of my first link. Suppose I represent that as a zonotope as well. Well, then now what I can do is I can translate my joint reachable set into a set of rotation matrices. Okay, and that's all I'm doing is basically taking these sines and cosines and turning them into the appropriate rotation matrix, which I'm going to denote by a capital M. And so that joint reachable set is then translated into a matrix zonotope. And now all I need to do is multiply that matrix zonotope by the zonotope representing the link volume. And essentially what I can show is that the matrix zonotope reachable set over approximates the rotation matrix reachable set. And in fact, what that means in practice is that I can actually construct the link volume as a function of time for the first link. And in fact, I can repeat that exercise to compute the origin of the second link of the system by just looking at the end effector of the first link and multiplying the appropriate rotation matrices here. And this allows us to get the translation of the second link due to the first link. And then I can actually do the same type of operation as I described earlier to describe the link volume of the second link. And then basically do this sort of addition operation to describe what the volume of the second link is. All of these operations are linear once I have the joint reachable set. So nothing nasty is happening here. So this is really a nice representation for the behavior of the system as a function of time. Again, my students like naming things very sillily. They call these objects rotatotopes because, who wouldn't? And we can keep doing this sort of operation. And essentially, these rotatotopes can be sliced to get the zonotopes containing the swept volume. And in fact, we have a representation of the swept volume here, which is truly an outer approximation to the swept volume of the system. All right. So now we can slice a rotatotope to get a zonotope containing the swept volume for a particular value of k. It's going to look like this. And I'm showing this just at a particular instance in time. You can do this for all time. It would just be a chaotic looking object. So keeping things simple. The question now is, how do I, intersect an obstacle with this, with the sliced rotatotope? And the thing here is that Zonotope intersection is a really nice operation, and that's what really allows us to do nice things. So if I represent my obstacles as zonotopes, and I can conservatively represent my obstacles as zonotopes, may have lots of them. This doesn't mean that my obstacles have to be convex. In fact, they can, be any shape, and I would just be representing them with a set of zonotopes in that instance. Well, now if I want to determine if these two zonotopes intersect with one another, well, that corresponds to me checking that the center of one is inside of this new zonotope constructed by taking the generators of the first zonotope and essentially adding it or appending it to the second zonotope's representation. And in fact, I can represent this operation using a Minkowski sum. Okay, this is a lot of math. Let's take a look at what it looks like pictorially. So if I call this my first zonotope and I call this my second zonotope, what I'm essentially doing is taking the generators of this first zonotope and essentially adding it to the second zonotope. Okay, and then basically checking to see if the center is inside of this new, larger looking set. Okay, and that's a nice operation for me to write down as it'll turn out. Okay, so I'm basically determining if this guy can be inside of this guy. And in fact, that operation is something that looks like this. I'm basically checking that the generators of a particular link volume do not vary with K. And this is it'll turn out that the position of the center depends only linearly on K. This is a theorem that's inside of our RSS paper. What that means in practice is that I can write down this constraint in a nice, very linear-ish looking way. So in fact, I can represent this obstacle as the following in A obs and B obs, which is sort of a linear representation for the obstacle. And in fact, in practice, I can write down the collision avoidance as a max over a set of linear constraints. So essentially, if the max over a set of linear constraints is less than 0, then this means that K is safe. And in fact, what that means in practice is that this optimization problem is going to look like this. And in fact, this is going to allow us to use like really nice subgradient techniques to write down a derivative for this. And in fact, all of this optimization can be done in a really nice way, meaning gradients and everything can be handled. It's not linear or it's not a convex program, but it's as close as you can probably get without it being convex in this instance. And that allows us to write down a really nice optimization problem that we can solve at runtime. And in fact, self-intersection, joint limits, and actuation constraints can all be written down in a similar way in this instance. And in fact, you can show that if you find a feasible solution to this optimization problem, the robot will not crash. And if you plan in a receding horizon way, where if you don't find a feasible solution, you continue to apply the solution you computed that was safe in the previous instance in time, you can show that the robot will always stay persistently feasible and will always stay safe in this instance. So what does this look like? Here's sort of a challenging situation for most robot manipulation. It's a really thin obstacle. And in this instance, we have a target configuration that we'd like to get up here. And you can show, really nice things happening. I should pause this video here. You'll see sort of the reachable set of the system. The trajectory parameterized reachable set is drawn in this black around the current configuration, which is blue. You'll see sort of this light black thing over here. That's actually the waypoint that, is generated by an RRT, which is we're trying to track. And the goal configuration here is in green. Okay, and so you can see sometimes, this black thing here, which is a waypoint, is in collision, right? But nevertheless, our robot is always able to find a safe solution. Sorry, too aggressive here. Okay, and so you'll see slowly it's able to get to the top. And, it takes a second here. You can do it. So the waypoints we're generating in this instance are not particularly good, but nevertheless, we're actually able to generate a safe trajectory. It's all done at runtime. The cool thing here is, again, we can do this for dynamic obstacles as well. So for example, if I have this fancy vase pops up, we can actually, again, because we're planning in real time, avoid it in a nice way. All the code that we've developed, by the way, is down here. So if you want to click on that, play around with it, let us know if things are broken and whatnot. I'll mention, again, this method. I've just shown it for sort of this manipulator case. We've actually extended it to a bunch of different systems. we've compared it to lots of different systems. So here's a Segway robot. We're using nonlinear model predictive control built around GPOPS2. We compare how often things crash or how often they get to a goal. RTD is always able to avoid crashing because we have these really nice persistent feasibility requirements. And so I won't even plot the crashes for RTD because there are none, right? And so the thing we want to show here is that we're not conservative. We generate these really tight reachable sets that allow us to plan without introducing additional conservativeness into the system. We've done lots of comparisons here to lots of different systems. And so, for example, we've even compared to Fast Track and Chomp, which are other methods that exist out there. We've done comparisons to sort of state lattice methods, linear MPC methods, all sorts of stuff. Sort of the only place where we've lost in terms of being less conservative is this RRT method using a rover. This is actually using an old technique for reachable set construction. So we're actually probably a little bit better now, but I will point out that they have crashes, which is a serious problem for them. And as I mentioned, we've actually been able to apply this. I think this is up to date from last year. We've actually been able to apply this to a lot more systems as well. I'll pause here for a second. Jana, you guys only go until you guys only go until 3:50, right?
We go till 4.
Okay.
And that includes question and answers.
Okay. Well, maybe I'll pause here for a second and maybe I'll take questions. If I don't cover this Kutman-based stuff, it's totally fine. So if anyone has any questions, happy to start answering them now. And then if we have no questions, I'm happy to talk about this last part, but otherwise I'm happy to hold off on that if there are questions.
That sounds great. I'm gonna pause recording so people.
Is it good for me to keep going? Okay, great. So we're going to talk about this Kutman-based modeling. It's going to be sort of short here. So the thing to keep in mind is soft robots are really difficult to model. They're difficult to model because they have these continuous deformations, distributed actuation, and the nonlinear material properties are pretty challenging to describe in a concise way. This is my student Dan. It's primarily his work. I'll show this funny video of him just to illustrate how difficult it is to control. So he's trying to do this by hand. And there are even funnier videos of him having the thing run into his face repeatedly. It's challenging to make these types of systems work well. So what we're going to try to do is develop a method that can do data-driven modeling of these types of systems, and in fact, that's going to allow us to do real-time control of these types of systems, even in the presence of loading. The idea is actually going to be, again, really similar to what I presented earlier. We're going to apply a lift. As I mentioned, we're going to allow this lift to be truly sort of more representative of the system rather than sort of stopping the lift at sort of 2 basis functions. And the idea here is, many people have seen sort of SVM classifiers maybe. So like if I have an SVM, I have some data here. In linear SVM technique, I can write down sort of the classification problem. So for example, if I wanted to represent the red points here as 0 and the blue points here as 1, well, I can write down a linear program that basically generates a separating hyperplane here that separates the 2 pieces of data. And that hyperplane allows me to write down sort of a linear representation where everything over here on the left-hand side may be greater than 0 and everything over here on the right-hand side may be less than 0. Now, the challenge is, of course, when the data looks more complicated, lots of bad things start happening because I can't do anything nice here, except I can. And the way that I can is by basically lifting the data here. And this lift here now basically translates the data into something where I can, again, apply, a linear SVM. And so people typically call this, the kernel trick, right? And in fact, in a lot of ways, what I did in the first portion of the talk was like applying a kernel trick to allowing me to compute the reachable set elegantly. In practice, again, what we're going to try to do is to do the same thing with dynamics, which is, again, trying to lift the dynamics so that things look linear here. And I'm going to focus primarily on being able to do this in a way that allows me to apply sort of linear MPC style techniques to control the system. So the way that it's going to look is the following. So suppose I have a nonlinear dynamical system. I can write down the dynamics here and I can describe the flow map of the system. So, what that means is the flow map, is describing the evolution of the system at these finite instances in time. Okay. And so now I can, keep doing that and extend it out, further and further and further. And what I can write down is this thing called the Kutman operator, which describes the application of this operator to functions, right? And the way that it's going to be defined is in the following way. So I'm going to take that function and I'm going to compose it with this flow map that I defined. what that means in practice is I'm essentially taking my system that looks, down here in finite dimensions, and I'm going to essentially understand the behavior of the system on functions evaluated on the dynamics, or functions evaluated on the state space of the system. And so it's going to basically look like this. And in fact, the great thing is that, this representation of the nonlinear dynamics by looking at its application on functions of the state space is actually going to be linear, okay? And it's going to describe or summarize the behavior of the nonlinear system. But the trade is everything is going to be infinite dimensional now rather than being finite. So one way of thinking of this is I'm really taking that kernel trick that I described in the second portion of my talk and really taking it to its extreme. Now, the challenge here is, how do I represent this object? And the thing is, I can represent it by basically looking at a finite set of basis functions and describing sort of the evaluation of this Kutman matrix on that finite basis function set. So one way to think of that is that, I can have a representation of my function with respect to my basis function set. So some arbitrary function, I can project it onto my basis function set that's going to generate some sort of vector representation of my function with respect to my basis function set. And in fact, I can think of the Kutman operator as if it acts on this projection of this basis function, or projection of the function on this basis function set. And so, in fact, that's this operator that we're going to generate. The thing is, that operator may not necessarily allow me to, though it's linear, it may not allow me to do optimization in a really nice way. So I'm going to think of applying this Kutman operator to some subset of all possible basis functions where that subset is going to allow me to do nice things with respect to control. Okay, and so that's basically the idea of this section. So I'll have my state space model. It's collecting data. I'm going to translate that data by applying a lift, and I'm not going to consider arbitrary lifts of both the states and the control. I'm going to focus on lifts that look of the following form. So in particular, I'm going to apply a lift on all of the state space, but not on the input space. Okay. And in fact, what I'm going to do then is identify the Kutman operator, but just on this subset of basis functions. What that means in practice is that I'm going to try to identify a linear time invariant model matrix. And because I'm not lifting all of the input, but I'm allowing the input to sort of pass through without lifting, I'm actually going to be able to extract a control matrix here and a state space matrix, or state matrix here that are going to be represented as LTI. And in fact, that's going to allow me to write down an LTI model representation for this nonlinear system. We can show that this is going to allow us to do something like linear model predictive control. But in fact, the thing is, you can't prove that this representation is perfectly accurate as you can with the Kutman matrix. But because I'm not lifting everything, I'm just lifting a subset of functions. But nevertheless, this is going to be good enough for us to actually be able to control and model the soft robot. And that's the thing that I care the most about in this section. And so, we've shown that we can do this. I'll sort of skip ahead here and just show the videos. So this is us applying an MPC controller to try and do tracking of a particular trajectory. This is all running in real time. And this is us trying to track this particular trajectory of the system. And, this is kind of cool. Again, doing this type of control is really challenging with these robots. And I'll show you sort of what other methods have been able to do in comparison. I draw these gray lines here. It turns out that, we have sort of not very precise control of the actuators here. And that's just because of the way that pressure regulators work. So you can actually measure the actuation sort of precision of these pressure regulators. And in fact, this MPC controller is within sort of the precision limits of what this actuator is capable of commanding. And in fact, we've actually been able to extend it to doing sort of more complicated things like actually doing sort of pick and place tasks with these soft robots. And in that instance, we're lifting something slightly different than what I described earlier, which is we're lifting also the weight of the system. And in fact, we can do sort of a Leuenberger style weight estimation on the lifted space in a nice way. And you can find the details down here. But in practice, that allows us to do things like being able to determine the weight that we have of an object down here at the bottom by basically moving the robot around. And that allows us to do sort of precision, sort of pick and place. we're working on more complicated things. So like being able to throw accurately and whatnot. So keep an eye out. We'll hopefully have something to show in the next few months on that front as well. And that's sort of all for this section. I'll sort of skip ahead here just so that people can sort of see it doing all sorts of stuff here. It's able to actually even, precisely figure out what the weight it thinks is. And we actually have some stuff in the paper that it's actually converging to the correct weight as well, or within sort of, 2 or 3 grams of the correct weight in this instance. So that's sort of all I have. And again, I'll mention these are sort of the students who are actually doing all of the heavy lifting. These are our sponsors who are actually, making all this work possible. I will point this out maybe in the next slide as well. You can find all of the code that I presented about down here. Take a look, play around with it. We want to find things breaking, whatnot, and learn more about how to make things better. So feel free to download and try stuff out. We've also tried our best to post, examples of things that we've run in the papers. So, and data for the soft robot, for example, some people have been interested in that. Take a look and let us know if you find anything interesting. But sort of that's all I have for today.